So today we will start a new topic. We will move to the second unit. Stability of the system is a very important topic. So before going into the stability, first of all, we will summarize the first unit. We started with control system, right? We have seen what is a system, what is a control, and why control is required in a system. We have seen different examples, right? Open loop as well as closed loop systems, right? Then we have concluded that in order to design a good controller for a system, first of all, we need a mathematical model. So after getting the mathematical model, we have to analyze the performance of the system. Analyze in the sense we have to check the stability of the system. Then using different test signals, we can check the expected output, right? Test signal in the sense, what are the common test signals used in a control system? Step signal, impulse signal, ramp signal, then sinusoidal signals, right? These are the four signals. And one more signal is there, parabolic signal. Anyway, we will see in the coming unit. And then we have seen how to model a system using the mathematical concept, right? That means all systems are having a linear ordinary differential equation. So from that linear ODEs, we can derive our mathematical model, right? And then we have seen transfer function. Transfer function is nothing but we can convert the time domain differential equations to a polynomial, which is in the S domain using the Laplace transform concept. And the transfer function is nothing but it is the Laplace transform of the output divided by Laplace transform of the output, maintaining all the initial conditions 0, right? So if you give a test signal and if you are checking the system and if you see the output response can be divided into two parts. One is free response, other one is forced response. Free response is response due to the initial condition, and the final forced response is the response due to input. And further, we have seen how to reduce it. Suppose I have a big plant having a lot of blocks, how to reduce that blocks into a single transfer function using some fundamental rules. Then we have seen signal flow graph. If you have a complicated system, that particular block diagram can be converted into signal flow graph form. So using Mason's rule, we can reduce that system to a single transformation. So these are the things we have seen. So this unit we will discuss what do you mean by stability of a system, when a system is, because in order to design a good controller for the system, first of all we have to check whether the system is stable or not. If the system is not stable, we are not able to design a controller. So for that we have to see the concept of stability. So in order to study the stability of the system, again we will recap some few things from the transfer function. So we have seen the transfer function of a system P of S is the Laplace transform of output divided by Laplace transform of input. Some case we will represent y of t, c of t, something like that. In general, we will represent output as y, input as u. So we can write y of s divided by u of s, keeping all initial conditions 0. right? Then for a mass spring damper system, we have derived the transfer function, right? For a mass spring damper system, what was the transfer function? Suppose we have, yes, mass spring damper arrangement like this. Let it become, this is K, this is B. If I am applying the force F of T, so let X of T be the output displacement. One second, one second. Is it okay now? Okay. So this is a mass spring damper arrangement, and we have derived the transfer function for this particular system, and we got the transfer function as x of s divided by f of s is equal to 1 divided by m s square plus b s plus k. Right. This already we have seen this one. And what is the order of this system? This is a second order system. Right. So suppose now we will generalize the definition of the transfer function. So suppose I have n order system. So in general, we can write in general given equation of a nth order seesaw LPA system. How can we write? So in general, we can write like this because the transfer function is having numerator and numerator polynomial as well as denominator polynomial. So in general, we can write a naught. In time domain, we can write a naught d raised to n y of t divided by d raised to n plus a1 d or n minus 1 of y of t divided by d n minus 1. So, voice is clear only, right?
Yes, sir.
Check it now. Is it okay now? So in general, we can write like this, etc. plus a n minus 1 d of y of t divided by dt plus a naught y of t. Right. Where y of t is the input, right? And is equal to right side also polynomials will be there. So we can write d naught d power m u of t divided by d power mt plus d1 d power n minus 1 p of t by d power n minus 1 t plus etc. up to b m minus 1. This is not m.
Sir, presentation is again stuck, sir.
Again, I'll share the full screen. See. Check it now. Is it okay now?
No, sir, it's not visible.
For me, this shade. Okay, okay, it is coming again. Sorry. I think now it is okay. Yeah. So we can write b m minus 1 d p of t divided by dt plus bm p of t, right? So in general, for an nth order system, we can represent like this, where a naught, a1, an minus 1, an are the, here this is not a naught, this n, are the constant coefficients, right? So if a naught, a1, an minus 1, an are constant, we can call it as a time invariant system. If these constants are, if this coefficient of this expression is a variable of time, it depends upon the time, we can call it as a time variable system. These things we have seen, right? So if we apply Laplace transform on this equation, what we get? Taking Laplace transform on both sides and apply zero initial conditions, right? And then only we will get the all transfer function. We can write as transfer function y of s is equal to I of s divided by u of s, which is equal to b naught s power m plus b1 s power m minus 1 plus etc. up to b m minus 1 s plus bm, right? The whole divided by a naught s raised to n plus a1 s raised to n minus 1 plus etc. up to a n minus 1 s plus a n. Right. So this will be the generalized transfer function for an nth order system. Right. So we are having, if you see the final transfer function, it is having a numerator polynomial as well as a denominator polynomial. So we can write like this: g of s, the transfer function g of s is equal to n of s divided by d of s, where n of s represents the numerator polynomial. Check it now. உங்களுக்கு எந்த ஒரு document? Could you please this also PDF after the class? Yes, sir, yes, yes. I will share with you. Once anyway, first unit is completed, right? So I will send you. Don't worry. Okay. What about the presentation? Is it okay now? Shall we continue? Yeah. And one more thing is these details. Actually, I have taken from the NPTEL video. You can refer the video also. By Professor C.S. Shankarma. Is clearly explained about the concept, this concept. Okay, you can see this in detail video also reference. Okay. Okay, anyway, we will continue the course. So, it is having a numerator polynomial of order. What is order of the numerator polynomial? This is m, right? And this is the denominator polynomial. Order of the denominator polynomial is n. And if you have a function like this, I think you might have studied in mathematical course also. If I take the roots of the numerator, what is the root of the numerator? Have you studied this? So how will you find the roots of this? I want to find the roots of numerator polynomial. How will you find this? Because I know the polynomial is b naught s power m plus b1 power m minus 1 plus etc. up to b m minus 1s plus bm can be equated to 0 and solve it, right? So you will get the roots, right? So that roots can be called as zeros of the transfer function. Okay. So if we equate numerator polynomial as 0, what will be the transfer function? Transfer function become 0, right? Yeah. So we can call the corresponding roots as zeros of the transfer function. So this is very important. Keep in mind. Hereafter we will this word we will frequently will use 0 and pole, right? And what about the denominator roots? Denominator polynomial. If we find the roots of denominator polynomial, You might have studied that it can be called as, that root can be called as singular points, or another name is poles of the system. Right? So what is the denominator polynomial? How will we find the roots of denominator polynomial? Just equate to 0 and find the roots, right? So we can write b naught s raised to n plus, sorry, a naught s raised to n plus a1 s raised to n minus 1 plus etc. up to a n minus 1 s plus a n equal to 0. So if you equate this polynomial to 0 and find out, you will get some roots. That roots can be called as singular poles or points or poles of the system, right? So another way how we can tell it, we know we are in S domain, right? When T of S is in S domain in the sense S is equal to, it is having a real part and an imaginary part. So T of S is a complex valued function, right? So what do you mean by poles? So at certain points, there won't be any function or derivative of the function exist at certain points. That points is called singular points or poles, right? If you put d of s is equal to 0 in this transfer function, t of s become infinity, right? The value doesn't exist. So that roots are called poles of the transfer function. So we can summarize it. We can call the roots of the numerator polynomial of a transfer function as zeros of the transfer function, and the roots of the denominator polynomial of the transfer function can be called as the poles of the system. And we will see what is the importance of, what is the effect of pole and zeros in a system later. Okay. Now, another important topic, VIVO stability. VIVO stability. I have a system transfer function, and we have to see what do you mean by stability. VIVO in the sense bounded input, bounded output. Stability. Have you heard about this anywhere in network, signal cell system, or mathematics? Anywhere? Or first time you are seeing this? VIVO. You are studying, right? VIVO, right? Bounded input, bounded output. What VIVO stability is telling is, system is said to be stable if its output is bounded to all possible bounded input. So if I have a system and that system is producing bounded output for all the possible bounded inputs, we can call it as a stable system, right? In other words, we can tell for all t and u of t is the input, such that if this u of t is less than or equal to m less than infinity, we should have an output y of t less than or equal to n less than infinity. So this is the case where n and m are finite real numbers. So if I have a system, we are having some finite real number m as a input, the system also should produce an output having a finite number output n. So that corresponding system we can call it as a stable system. That is meant by bounded input, bounded output. For all the bounded inputs, the system should produce a bounded output. Then we can call it as a stable system. Okay. Now we will take one example and see the concept of stability in detail. Okay. I hope everyone understood what you mean by Vivo stability. If any doubt is there, please ask me. It's clear? Yeah. Suppose I have a system y double dot t plus 5 y dot t plus 6 y of t is equal to u of t. And another one more point I have to tell here. See here, m is the numerator polynomial order, and n is the denominator polynomial order, right? So if n is greater than or equal to m, we can call it as a proper transfer function. Please keep in mind, and you will see later. If n is greater than m, we can call it as a strictly proper transfer function. Strictly proper transfer function. So for a strictly proper transfer function, the order of the denominator should be higher than the denominator, the order of the numerator. Right? So if you take this example, what is the order of the numerator? M equal to 0, but n equal to 2. Right? That means n is greater than m. This is a strictly proper transfer function. Okay. So I have a system like this. First of all, I want where y of t is the input, u of t is the output. Okay. So I want to, first of all, I want to derive the transfer function model. How to derive it? Y double dot t means, I already told you, double dot means it is d square y of t divided by dt square. Y single dot t is dy by dt. So if I take, if I apply Laplace transform, we can write this as s square minus y of that initially. See, anyway, I am going to deal with transfer function only. So we don't need to hereafter. We don't need to write the initial condition, right? Because it is 0 only, obviously. So directly I can write x square into y of s plus 5 y dot t can be written as s multiplied by y of s plus 6 multiplied by y of s equal to u of s. So if I rearrange this equation, we can obtain the transfer function model. Is y of s divided by u of s is equal to 1 divided by x square plus 5s plus 6. Right? So this is the planned model for this particular system, where m equal to 0, n equal to 2. This is also a second order system where n is greater than m. So this is also a strictly proper transfer function. Right. Now, so this is the transfer function T of S. Now I want to find the poles and zeros of this. So how many zeros present in this system? Our numerator polynomial is 1. There is no S part, right? Because M is 0. So in this, for this plan, there is no zeros, right? How will you find the poles? In order to find the pole, you have to equate the denominator polynomial to 0, right? Denominator polynomial d of s is nothing but s square plus 5s plus 6. It can be equated to 0 so that I can find the roots. So it will become s plus 2 multiplied by s plus 3 equal to 0. So I have two poles. Let it be, first pole is s1, which is equal to minus 2, and the second pole is minus 3. Clear? There is no zeros in this system, but I have two poles having values minus 2 and minus 3. So how we can draw the location of these poles and zeros in the S-plane? So S-plane is having a real part as well as imaginary part. So this is the origin. So where will be the location of these poles? Usually poles will be represented as cross symbol. Zeros can be represented as a small circle. Okay. So in this problem, we are having two poles, one at minus 2. Minus 2 means left hand side of the S-plane, right? Let it be somewhere here. It is minus 2. And the another pole is at minus 3. So this can be, if you see a cross symbol, it means pole, right? 0 is not confused with this zeros and origin, right? Origin also will represent like this. Since we don't have any zeros, we don't need to mark it, right? So this is the representation of pole and zero in the S-plane, right? Now, I have to check the stability of the system. So for that, what is the definition? The output of the system should produce a bounded output for all possible bounded input, right? And for test signals, we have studied 4 important test signals, right? That is step signal, impulse signal, ramp, and sinusoidal signal, right? That ramp will represent as T, right? So this, out of this step signal and sinusoidal signals are the bounded inputs. Because in order to check the stability, we have to check whether the system produces bounded output for all the possible bounded input, right? If the input itself not bounded, means we don't need to give. These two signals are unbounded inputs. So in order to check the stability, we don't need to consider the impulse signal and ramp signal. We only used to consider step as well as sinusoidal signal. Sinusoidal signal is also a bounded input signal. It's an unbounded input signal. Okay. Now find the step response for this. Find the unit step response. How will you find the unit step response? Unit step response is the output produced by the system when the system input is a unit step input, right? I have the system transfer function y of s divided by u of s is equal to 1 divided by x square plus 5 plus 6. So how will you find the step response? How will you find the step response? Because step response means, yeah, our aim is to find y of t, right? Response in the time domain. For that, first of all, we will write the system output in s domain. So it can be written as u of s multiplied by x square plus 5s plus 6. So what is u of s? Because our aim is to find the
1 by
unit
s.
step input. So our input is 1 unit step input. So Laplace transform of unit step input is 1 by s. So we can write y of s is equal to 1 by s multiplied by this polynomial can be written as s plus 2 into s plus 3, right? So in order to find y of t, first of all, I have to apply the partial fraction, right? So applying partial fraction, we can write, right? Partial fraction method, we can write y of s is equal to a by s plus b by s plus 2 plus c divided by s plus 3, where a, b and c are called residues of the system. So next step is to find out a, b and c, right? How will you find a, b and c? Just take the LCM and set s equal to 0, s equal to minus 2 and s equal to minus 3. Can you please find and tell me what is a, b and c? I'll give 2 minutes. First, in order to find a, first set s equal to 0. Then find b by setting s equal to minus 2, and you can find c by setting s equal to minus 3. So what are the values of residues? A equal to 1 by 6, b equal to minus 1 by 2. Find. What about c?
1 by 3, sir.
Okay. So hope everyone know how to do this, and everyone is doing. Hope everyone is doing also. So after getting the residues, we can write y of s is equal to 1 by 6s plus minus 1 by 2 s plus 2 plus 1 by 3 s plus 3. So how to find the final response, unit step response? Take the inverse Laplace transform, right? So taking inverse Laplace transform, we can write y of t is equal to 1 by 6. Laplace inverse of 1 by s is 1, right? So 1 by 6 plus, this will come. So Laplace inverse of s plus 2 is 1 by s plus 2 is e power minus 2. So we can write minus 1 by 2 e power minus 2t plus 1 by 3 e power minus 3. So this is the unit step response of this particular system. Unit step response. Okay. Now we see what are the observations from this result. Can you tell, after seeing this final unit step response, what are the things you have noticed? Because I have the system, it is having the poles -2, -3, right? So regarding stability, whether the system is giving bound output for all time t, because my signal is like this, right? Is u of t 1 t. So this is a bounded input. If I give this, what we have to tell, if t tends to 0, sorry, t tends to infinity, that only we have to find, right? What about y of t? I know the expression, it is 1/6 minus 1/2 e to power -2t plus 1/3 e to power -3t. So if t tends to infinity in this relation, what is the y of t? What is the value of y of t? Yeah, y of t is 1/6. That means it is a bounded output. Right, it is a finite real number only. So the one of the important observation is the magnitude of y of t is bounded for all t. Right? Correctly, right? Yeah. Now, what about the exponents of the exponential time? I have two exponential times, right? Exponents in the sense, suppose I have a exponential time e power at. Exponent is a, right? Exponent equal to a. So while seeing this, can you relate anything with poles? In this case, I have two exponents. Yeah, correct. So the exponents are -2 and -3, right? The exponents of this relation is -2 and -3. What you already seen, the poles of the given system is also -2 and -3. So we can conclude in general the real part, right? See, poles are, see, we are converting all those things in S domain, right? Complex domain. So the pole is having real part as well as imaginary part. But in our case, it is only real part, right? -2 is the real part of the pole, -3 is also the real part of the pole. So we can generalize like this: the real part of the pole is appearing as the exponents. Right? So these are the two observations from this analysis. There is one important observation is for all the for all t, for this bounded input, the output is also bounded, and also the exponents observed in the output response is the real part of the code. Right? So whether the system is stable or unstable according to Weibo stability.
Stable, sir.
Yeah. So according to Weibo stability concept, the given system is stable. And another one more thing I have to tell is, what is the steady state value of this system? Steady state value, because if I draw the waveform, if I taking 1/6, right? Steady state in the sense t tends to infinity. So when t tends to infinity, the steady state value of this system is 0. That means y of t at t equal to infinity is equal to 1/6. So this is called, this is the steady state part of the system. What about the initial value of the system? Means at time t equal to 0, what is the y of t?
0, sir.
0, because we already mentioned that all the initial conditions are 0. All the initial conditions are 0 in the sense there is no free response. So obviously, if you draw t versus y of t graph, the curve will start at origin, right? Start from origin, and it will, if time goes, it will end at a value 1/6. So this is the steady state value. So after that, it will be constant, right? So what is happening between this point? What will be the expected shape? It's the exponentially rising waveform, right? Anyway, this we will see in detail in the coming unit. So don't worry. So steady state value is the value after reaching the steady state. So the output will be constant during this part. So this we will call as transient part. Anyway, this we will see in detail. Transient part. This is the steady state part. Okay. Anyway, we will summarize it and wind up the class. So according to Weber stability, we need to check whether the system is producing bounded output for all the possible bounded inputs, so that if you have a system, just apply the unit step input or sinusoidal signal. Just now we have applied unit step input signal to the system, and we have obtained that y of t is equal to 1/6 minus 2 exponential terms also there. So one important observation is the exponents in the y of t refers to the real part of the pole, and also magnitude of y of t is bounded for all t, and the steady state value can be obtained by setting t is equal to infinity is obtained as 1/6. And according to the Weber stability theory, the given system is a stable system. Okay. And I want to ask one question. Whether you need this document now or after completing the course, shall I send? Otherwise, I can do one thing. Anyway, we have completed unit 1, right? I will send unit 1 today. Remaining after completing the unit 2, at the end of each unit, I will send this document. Okay, is it okay?
Okay.
Okay. Because I will make all in separate sheet and send you. Okay, so today's class we can stop here. Okay, we will start tomorrow. So 10:30 I won't be taking class because I have some other meeting. Okay. Okay, thank you. We will see you tomorrow.
Thank you, sir.
Thank you, sir.
Thank you, sir.